All right, continuing the economist block for the morning, we have Denis Nekipelov. He's a professor of both economics and computer science at the University of Virginia, where he's also on the board of the data science program. He's a total beast. He's also someone I met in undergrad. I don't know if he remembers it, but he came and gave some very, very preliminary presentation of the work he and Susan were doing when I was in college. And I remember watching and thinking, wow, this guy's really cool. And so it's been really exciting to continue to get to know him over the ensuing years. And we're very excited to have him here to speak on robust empirical evaluation of large competitive markets.
Can you hear me? Okay, good. It works. Well, thank you so much for this wonderful introduction, and I really appreciate the organizers for the fantastic conference. The work that I'm going to talk about today is going to be joined with my computer science colleagues, Eva Tardush and Vasily Sarkanis from Cornell, Daryl Hoy and Jason Hartline from Northwestern, and Shuchi Chalais from Wisconsin. And of course, a lot of the insights that I have about the advertising markets, about which I'm going to talk about, are coming from my work with Susan Athey. Just to kind of fold this into the theme of the conference, I think that today and yesterday, a lot of the talks have been mentioning developing general scalable methods that are applying statistical inference to very large data. And one of the kind of key insights of my talk, hopefully, is going to be that if we combine that with domain knowledge and we combine approximation with theory, with statistical inference, we can actually get a lot further, and we can get actually the techniques that are going to be a lot better performing than the techniques that are sort of coming from the boilerplate of techniques. And the applications to these large markets are going to be mainly concerning the advertising markets and specifically sponsored search advertising, and I'm going to give you a little bit of a taste of how those techniques apply to those markets. So when we think about the kind of the majority of the data work in the realm of big data that economists have been doing, I would say that mostly it's related to the internet data. So this is the data from various consumer platforms. This is the data from advertising platforms. And if we think about the operational cycle of a lot of those platforms, is that everything is based on trying to roll out a new design, test it, optimizing the design, and then kind of doing the cycle again and again. So there is a constant testing, and there is a lot of tests that are simultaneously running on those platforms. And the kind of the very unique feature of the platforms that are involving the human subjects or economic subjects in general is that a lot of the designs that we're thinking as being kind of exogenous in the engineering sense, they're going to actually change the behavior of the platform. So this is something that Susan has mentioned before. So if we're going to change the settings of an auction platform, then the system may actually shift to a new equilibrium, and our results are going to be completely unpredictable unless we have an underlying theory. So another issue that arises in this large industrial platforms is that it's really hard to separate treatment and control. So for instance, the experiments that are done on the advertising platforms, the source of experimentation is going to be the randomization of the user queries. And so as a result, if our object of interest is the behavior of advertisers, the advertisers actually do not have the choice of which query they're going to appear. Well, they can apply targeting, but on top of that, they can really not use any other techniques. And so as a result, treatment and control are going to be really tightly combined. And so now the fundamental challenge that we're going to face in this context is that we want to somehow bootstrap the information about that unknown new environment that we're trying to test out using the data. Or in other words, we want to make inference regarding the object of interest. So the talk today is going to be entirely based on the auction design. And one thing that I want to mention before going into detail is that we're going to be focusing on very, very narrow goals. So we're not going to be just interested in inference in auctions per se. We're going to be interested in inferring the auction outcome. So we're going to be interested in making inferences for what the revenue is going to be when we change the platform, or what the welfare of the participants is going to be once we change the platform. And that goal is going to be fixed and concrete. So we're not going to be kind of changing that goal below our feet. So, well, first of all, just kind of to give a general introduction, given the interdisciplinary audience here. So why are auctions so popular? And the auctions are popular, especially in this very rich markets, is because this is a very, very flexible technology that, first of all, it works very quickly, so you can price your products instantly, essentially. Second, it actually scales very well, so you can roll it out on large markets, and it's going to perform beautifully well. It requires really minimal inputs from the participants. So in the sponsored search advertising auctions, the only thing you need to submit is going to be your bid for a particular keyword. You don't need to submit your demand schedule or some other characteristics. So it's very, very simple. And finally, the economic theory actually has very useful results that are stating that certain auction designs are going to be optimal, certain auction designs are going to perform better than the others. And so as a result, there's the combination of this nice properties actually explains, I think, to a large extent that a lot of the large companies and a lot of the products are now sold through some auction systems. So let me just give you the motivated example before going into kind of a harder theory. So let's suppose that we're going to work with the sponsored search advertising. So sponsored search links are appearing besides the organic search results on Google and Bing. And you can see that those links are ranked. Essentially, we have the mainline ads. And let me see whether I can use this pointer. I don't know what to. This? I don't want to blind anybody. OK. So, so you can see that we have a block of the mainline ads, and we have a block of the sidebar ads. And the interesting feature of the structure is that the ads are actually naturally rankable. So we have this very nice rank structure here. And so the question that arises in this context is, can we re-optimize the design? So we run an auction, we allocate and we price all of those advertising slots. And the next question we want to ask is, well, can we actually change the page configuration in order to serve some revenue or welfare goals? So for instance, can we actually increase the number of mainline ads, and is it going to increase the auction revenue? Or consumers are going to be completely turned off because there's too many ads? So now the question is going to be, how do we compare between two different auction designs? And the goal at this point is going to be revenue. We can similarly talk about welfare, but I'm going to focus primarily on revenues. And so the approach to that, and this is the standard approach in the industry, we're going to run an A/B test. So we're going to randomize consumer traffic, and we're going to expose our users to different auction designs. The users are going to respond in a way, so we're going to see the response in the clicks in the click side. So the user is going to see one of the A or B designs, and then we're going to measure whether the click-through rates in the two designs are going to be different. Another side of the story is going to be the auction revenue. So we're going to have the bids that are submitted for particular keywords from the advertisers. We're going to look at the auction outcomes that are going to be based on clicks. So a lot of the payments in this realm are based on consumer clicks. So once the consumer clicks, the payment is going to be transmitted from the particular advertiser. And then we're going to have to compare which design of the auction is going to be more revenue generating. And so as I mentioned before, the issue in this randomized world is that given that we're randomizing on the user queries, and the advertisers themselves actually have no way of excluding themselves from particular queries other than targeting, what we're going to see in the end, once we run this experiment, is really going to be some third auction design, which is going to be a mixture of the two auction designs. And so our goal as economic theorists is going to be to try to bootstrap the outcome of the auction that we were interested in testing from this mixture of the two auctions. So as a result, the questions that we're going to raise here is, first of all, this is going to be the question of counterfactual prediction. So given the data that's going to come from the combined auction design C, we want to infer what is going to be the revenue of some auction A. And the other question we also could be interested in is going to be the question of, can we actually design an optimal auction given the data that's going to come from this combination of auctions? So the requirements that we're going to impose on the answer that we're going to provide are going to be, well, these are going to be the feasibility requirements. So we want our technology to be useful. So we want the outcome to be, we want our procedure to be computationally efficient. So we don't want to work with complicated computational problems. We want it to be scalable, so we want it to work on small and large markets equally well. And what's even more important, we want it to be also very robust to the underlying assumptions. So in some sense, we don't want our economic theory to completely drive the results that we're going to provide. So we want the data to somehow tell us what the actual outcome is. So throughout this talk, I'm going to talk about two particular implementations of the solution to this problem. So first, I'm going to talk about the inference that we can conduct if the agents in the platform converge to a Nash equilibrium. So it turns out to be the easiest case that we can conduct, and it's actually leading to a very, very nice technology for inference. And then in the last part of the talk, I'm going to talk about the inference that we can conduct if the system is in non-equilibrium conditions. So for instance, the agents are trying to learn the strategies, or there are new naive agents that are coming into the system, and we still want to provide some forms of guarantees for revenues or welfare for this platform. And so the main empirical illustration that I'm going to use is going to come from the sponsored search auction. So this is going to be kind of a very toy illustration. It's not kind of a platform-wide experiment. We just kind of try to show that what we're producing makes sense, and it actually produces reasonable results. OK, so now let's, Susan has wonderfully presented this earlier. So this is the question of counterfactual inference. So I'm kind of going to fold it back to her wonderful narrative. So basically, let's just think, or let me rather portray how the economists are going to think about the inference from the data if we want to infer something that we don't observe. So what we want to do is we want to build a model of how the agents are going to behave. And in this model, we're going to, in this case, assume equilibrium settings. So in equilibrium, the bidders are going to be happy with their bids. And if this is an equilibrium, then nobody has an incentive to deviate from the actual submitted bids that are submitted in the system. So one thing that we're kind of noticing in this context is that, well, if everybody has converged to an equilibrium, then the distribution of equilibrium bids is actually observed in the data. We don't even need to compute an equilibrium. We actually observe it. So as a result, the standard strategy for counterfactual analysis in this context is going to be, well, we're going to take the bid distribution. We know that everybody is going to be best responding to the bid distribution because it's an equilibrium bid distribution. We're going to construct the best responses. So these are going to be very simple empirical exercises. We're going to invert those best responses and then use the estimated values to do the new counterfactual prediction. So we will compute what's going to happen to the new equilibrium given the values that we estimate from the data. So this is a wonderful strategy. However, it really has some limitations, especially when we try to really scale it up to the big platforms. So first of all, when we think about the inference stage of the procedure, is the inference stage really requires us to estimate some form of a function. And so the more complicated the market is, the more complicated the function is. And so as a result, in order to have good statistical performance when we're trying to estimate that function, we actually will have to make assumptions. And those assumptions are going to be something like smoothness. So we want this function to have a certain number of derivatives, or it could be convexity, or some other assumptions in order for our statistical techniques to work. And what's even more concerning is that in most cases, especially when we're doing non-parametric inference, the statistical properties of our estimator are going to depend on the assumptions that we make. So basically, if something changes in terms of the function that we're estimating has not two but one derivative or has no derivatives, the properties of our estimator can actually drastically change. And so this is actually concerning in the sense that in a lot of cases, other than from assumption, we don't know how many derivatives a function has that we're estimating. The second problem is the computational one. So we are trying to use the values in order to compute the new counterfactual equilibrium. And it's actually been shown in a lot of game theoretic situations that computing equilibria is hard. So in fact, in many Nash equilibria, it's been shown that it's actually NP hard. And so what that means from the computational perspective is that, well, many approaches that we're going to implement in this way, they're just not going to scale very well. So we're not going to be able to predict for very, very large markets. So the question that we can pose in this setting is, well, can we actually avoid recovering preferences and go directly to inferring the object of interest? And as I said in the beginning, the object of interest is really going to be one parameter or some ratio of parameters. So this is going to be, say, revenue in the auction. So let's look at the auction environment, and I'm going to look at the rank-based auctions. So the rank-based auction operates in the following way. So that let's just assume that we have n bidders. Their values are drawn from some distribution, and those bidders are going to submit their bids. And the allocations of the goods to those bidders or clicks to those bidders are going to be based on their ranks. So we're going to just rank the bids, and whoever is the highest is going to get the biggest allocation, et cetera, et cetera. So why are we interested in the rank-based auctions? Well, we actually prove a little theorem which actually demonstrates that any auction with an exogenous allocation rule can be represented as a rank-based auction. So the theory that we're generating in this way is actually going to be pretty general. So just to give you a couple of examples, so for instance, the auction that Yahoo had originally run, the first price position auction, is going to have, say, k positions. Each position is going to have a different rank. Given that the different positions are receiving different clicks, they're going to correspond to those position weights. So this is a very classical rank-based auction. And you can see that special cases are, say, one-unit auction. So one-unit auction allocates everything to the first bidder. So we have basically position weight 1 for the first position and zeros for everything else. Multi-unit auctions are working in the same way. So now let's return back to the question of inferring the revenues. When we'll look at Meyerson's work, the revenue equivalence result is saying that when we're working with auctions with the same equilibrium outcomes, we should be expecting them to have the same revenues. So in that sense, if we're in the world of, say, second and first price auctions for a single item good, then we already have a very scalable algorithm for inferring the revenues of a second price auction if we observe the bids from the first price auction. We just compute the average. That's the most scalable technology we can get. Now, the problem with complicated rank-based auctions is that it's really hard for us to find such an equivalence in terms of the auction outcomes. And one thing that we notice in relation to those auctions is that they can really be easily represented as the linear combination of posted prices. So let's just think about this problem in terms of quantiles. So we rank our bids. So each bid is going to correspond to a particular quantile of the empirical distribution. And if we think about a take it or leave it offer, so if we assume that we have a fixed price, then all of the agents whose values are going to be above that fixed price are going to take that offer, and all of the agents whose values are below are not going to take the offer. So as a result, our expected revenue is going to be 1 minus q times the value that corresponds to the threshold quantile. So now if we have an auction with an arbitrary allocation rule, so we're going to have allocations according, across different quantiles, then the corresponding aggregate revenue is just going to represent it as this integral. So it's very simple. So this is basically weighted sum of take it or leave it offers. Okay? So this is nice and good, but you can see that it still requires us to infer values. So what we can do is going to be a very simple mathematical trick, which is to a large extent inspired by Meyerson's work. So I'm going to show how this trick works for the so-called all-pay auction. So the all-pay auction is the auction where we're going to solicit bids from everybody. Everybody is going to pay their bid, and then the allocations are going to be according to the ranks of the bidders. So the only reason why I'm using this format is because the algebra is a lot simpler. I just want to show it how this works in one page. So basically, what we can do is so we know that everybody is happy with their bids. So everybody is going to be maximizing their utility. The utility is going to be the probability of allocation times the value minus the price they pay, and everybody pays their bid. And so as a result, we can actually solve the first order condition and express the value. That value can then be substituted into the expression for the revenue of the auction, and then we do a simple integration by parts. So why is this formula exciting? So this is now the formula that's expressed in terms of the empirical quantiles. Well, we essentially got rid of the values. We don't have values anymore. So just to kind of show you the formula to highlight it, so essentially what we have here is a weighted order statistic of the observable empirical distribution of bids. So in order to infer the revenues of auction Y, if we have an allocation rule X, the only thing we need to do is we need to compute this object Z, rank the bids, and compute the reweighted bids. So this is going to be a very, very efficient way of producing counterfactual inferences if we're interested in revenues. And this scales wonderfully because, well, this is just a weighted average. One more thing which is very exciting about this technique is that this is actually a very robust estimator in the following sense. So the only thing we need here is the object that we actually observe. We don't need to estimate any functions. We don't need to fit anything. We don't need to cross-validate anything. We just need to compute an average. So basically, this is the approach that gives us the evaluation of the outcome given the input. So now let me just demonstrate to you a couple of results. And again, this is going to be the result in a simplified setting. So I'm going to look at a rank-based auction with an allocation rule X. And I'm going to try to infer the revenue of the k-unit auction, which we denoted pk. So in this case, we can actually provide a very nice tight uniform bound for the inferred revenues. And as complicated as it seems, the most important thing from my perspective here is the fact that we have the ratios of the slopes of the allocation rules. So let me just give you a couple of pointers here. So the first pointer is going to be if we're going to infer the revenues of the k-unit auction from the bids from the k-unit auction, we're going to get a nice uniform bound in that. So that's nice, and it actually makes sense. Now, if we're working with auctions that are going to be very, very similar, the thing that's going to be the most exciting, and I'm going to highlight it further, the thing that's going to be the most exciting is that the dependence is going to be, the dependence from the distance between the two allocation rules is going to be in terms of the logs of epsilon. And so as long as the two auctions are not too far apart, we're going to have very, very good properties of this combined error. And one thing that's even more exciting is that the dependence on the number of participants here is kind of very isomorphic to the dependence on the dimensionality in some of the problems that we considered before. So at worst, it's going to come as n log n in this case. So the bounds that we can provide for other auction formats are very similar. It's just the algebra is simpler. So believe me, it's not that much more complicated. It's just I wanted to avoid loads and loads of algebra. So this actually has very nice implications for how we can work with the actual industrial A/B tests. So if we're working with an A/B test where we have our control flight, we have our control auction design that basically is the auction design that is currently running in the system, we can mix in a little epsilon of the new auction design, and the dependence on that epsilon is going to be logarithmic. So basically, what this means is that our samples can be very, very tiny. without affecting the error significantly. Moreover, there's actually going to be a very nice trade-off in terms of the size of the control flight and the size of the experiment. So in the big data settings, given that our experiment is given that our control is going to be very large, our n is going to be very large, our error is going to be proportionally small because we have this n in the denominator. So this is a nice way to trade off the experiment sizes with very large samples. And so another thing that I wanted to say here is that we can actually contrast it very nicely with the kind of ideal A/B test settings. In the ideal A/B test settings, we actually have a treatment, and we have a control, and we have no model, right? So in that case, we are going to allocate epsilon of the traffic to our treatment, and the rest is going to be our control. So what that means is that the error is going to be proportional to the square root of the size of the treatment sample. So this means that the error is actually going to be geometric, not logarithmic, in the size of the control sample. OK, so we can also apply this to the auction design, not just to A/B test. I'm going to skip this for the time constraints. So one thing that I wanted to emphasize in this case is that this is all very beautiful, and it works very nicely. One very serious caveat, which is very, 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 very complicating a lot of the results, and this motivates a lot of the work that we've been doing with Susan Athey, is in a lot of these platforms, the behavior is very far from stable. And so it's unclear, unless we have a model, can we actually do something about predictions for, say, welfare or revenue? And just to give you an example, so this is a couple of patterns, a couple of pictures of patterns for a couple of keywords in the Bing system. So the bids are changing very rapidly, and these are telecom-related search phrases. I'm not going to tell which particular industry, but the patterns are kind of vary all over the place. There's a lot of experimentation. It's clear that there's no kind of stable fixed point that we expect when we talk about a Nash equilibrium. And also kind of another kind of pointer here is that a lot of the advertisers in this realm are using pretty sophisticated bidding tools, and those bidding tools are not explicitly stating that they're computing a best response. They're doing some kind of ROI optimization. We don't know what it is. So part of the work that we're doing with Susan Athey is actually trying to figure out what they're doing. So here, what we're trying to do is, if we are not assuming what they're doing, can we say something, maybe not very precise, but something about revenues and welfare of participants in those auctions? So the concept that turns out to be very, very useful is the concept of the price of anarchy. So the price of anarchy of a mechanism is essentially the ratio of the best case versus worst case scenario of the welfare of the mechanism. So we're comparing the welfare of the optimal mechanism with the welfare of the mechanism that we're running. And we're basically taking the worst case scenario over all possible value distributions, over all possible types of the participants. And so the implications of the price of anarchy, if we know it for a particular mechanism, is going to be the following. Well, first of all, if we know the price of anarchy, then we can actually characterize the sets of values of distributions of values that are compatible with this price of anarchy. Second, if we actually have an external way of producing the price of anarchy, then we can provide the bound on the welfare of our mechanism that actually is, again, going to be robust to the assumptions regarding the distributions of values. So we're not going to have to assume anything about the distribution of values. And so just to fold it into my previous discussion, our interest is going to be in the second. So we want to provide some forms of guarantees for the welfare in these auctions without making too many assumptions. So the useful concept that we're going to use in order to provide that external evaluation for the price of anarchy is going to be the concept of the revenue covering. So this is kind of a very rough kind of interpretation of what the revenue covering is. So let's assume that we have an auction where to win this auction, you're going to have to pay $1. we're going to say that this auction is going to be mu revenue covered if the expected revenue from that auction is going to be 1 over mu, at least 1 over mu. So why is revenue covering important? So if we're able to find this revenue covering parameter, then the previous work in the algorithmic game theory provides a very nice bound for the price of anarchy in terms of this revenue covering parameter. And it's also very interesting in the sense that for some auctions, we know that this revenue covering parameter exists and it's finite. And for some very important auctions, like the generalized second price auction that's run in most of the advertising platforms, this revenue covering parameter is not known, or it's known to be infinity. So one thing that's very exciting about this, though, is that revenue is something that we can measure directly in the data. And if we can measure something directly in the data, then we have a hope of having some kind of bound on this revenue covering parameter. And this is the augmented notion that we recently have introduced, which is called the empirical price of anarchy. So now, we are not in vacuum in any sense of form. So we actually have the data that comes from the platform. So why don't we combine the notion of the price of anarchy? And we're not going to just take the supremum over all possible distribution of values, but we're going to take the supremum over all distributions of values that could have generated the data that we observe. And so what's interesting about that is that distributions of say, bids that we're going to observe in the data are very well measurable. So we all know that there are very tight bounds for the inference of empirical distributions. And so as a result, we can hope that the parameter that we're going to estimate in the end is going to have very good statistical properties. So kind of folding back to the sponsored search auction, so we're going to talk about the sponsored search auction context. It's slightly different from the kind of the Bayesian auction context that I was introducing earlier, but it's actually similar. And one of the reasons why it's similar is that the sponsored search auctions actually have a lot of innate uncertainty. So one of the important goals in those auctions is the trade-off between revenue and relevance. And so as a result, not the bids that are taken into account in order to compute the allocations and prices are not going to be the raw bids. They're going to be the bids that are going to be weighted by the so-called scores or the relevance parameters. And those scores are going to vary significantly. Those are going to be very personalized items that are going to vary significantly from query to query. And now, in kind of this context, the auction is going to be run every time a user submits a search query. So everything is going to be ranked, allocated, and priced every time a user submits a search query. And so as a result, in my previous work with Susan Athey, we actually have shown that what that leads to is that a lot of the allocation curves that we're going to work with, they're going to work exactly similar to what we see in Bayesian settings. So we're going to have the relationship, in this case, this is a relationship between the price per click and the probability of click in the query. And that's going to give us some continuous curve. And so as a result, now, if we have a bidder with value v, then we have the corresponding utility, which is going to be the value minus the average cost per click. And this is going to be the amount of clicks that this bidder has bought in this auction. And the revenue is going to be computed in the same way. So the point here is that things are continuous, and that actually is going to help us a lot. So what this helps us with is kind of providing a more formal characterization of this revenue covering parameter. So we can look at this. So this is the price per click as a function of the probability of click. So we can just plot it by looking at the data. And then what we can determine here, so the revenue that we're going to have we're going to generate from this bidder corresponds to this rectangle. So the revenue covering parameter essentially is going to correspond to the ratio of the area of this rectangle and the area under this curve, which corresponds to the maximum amount of money that would be extracted from me if I slowly moved up a position, right? So basically, if I move up, I'm going to pay more and more and more, and I'm going to get additional clicks. Okay? So this has given us a very nice expression for the revenue covering parameter. And so now we're done. Why are we done? Because, well, we know exactly how this curve is going to look like once we go to the auction data. We can actually construct it without any data because we know exactly how the ads are going to be scored because we have access to the scoring algorithm. Now, for the revenues, the problem is going to be exactly similarly simple. So we just go to the data, we compute the sum of the bids times the scores times the click probabilities, and we're done. So this is the end of our exercise. So from that, we can estimate that threshold constant mu. That constant mu is going to be folded back into the bound for the price of anarchy, and that gives us the final outcome. So basically, this gives us the ratio between welfares or revenues in the case of an optimal auction versus the auction that we're currently running in the system. So now, going back and just to give you a couple of illustrations in the remaining 3 minutes, going back to the sponsored search auction. So the sponsored search auction is a version of the generalized second price auction. So the generalized second price auction is the rank-based auction. Everybody's going to be ranked. And then the prices are going to be determined by the bidders who are ranked below you. So basically, the bidder in the top position is going to pay the price that's determined by the bidder in the second position. And what's known from the theory perspective is that this is not revenue covered. However, it's not a problem for us, because even if it's not revenue covered in theory, we're going to revenue cover it in practice, because we can measure the revenue and we can measure those thresholds. So we're going to look at 11 isolated keywords. I'm not going to tell you which keywords they are, but they're pretty significantly isolated and pretty expensive. And for those keywords, we can construct those curves that I was showing you. So this is the price per click is on the x-axis, and the probability of click is on the y-axis. So we have those nice curves plotted. And so once we have those curves, we can actually compute our threshold functions, which are basically the integrals under those curves. So this gives us those very nice, very kind of smooth curves that we can use. And so the next exercise is going to be to look at this inequality and compute the maximum over all possible allocations of clicks given the thresholds. So basically, this is going to be a convex programming problem. Using the output from the convex programming problem, we're able to compute the constants mu, and as a result, we're able to compute the corresponding empirical price of anarchy. So why is this useful? Well, this is useful because it shows us how badly our auction mechanism is performing for particular keywords, right? So basically, what we see from this expression is that, well, most of the keywords are performing somewhat not too bad. So it's close to 1, so it's close to optimal. But there are 2 keywords that are performing really, really bad. So the price of anarchy is close to 4. So basically, this approach actually does not give us the precise expression for the counterfactual revenue or where the optimal is relative to the current, but it actually gives us a very quick diagnostic tool that we can run very quickly in the system and say which markets in the system are performing poorly. So I would like to summarize at this point. So the auction design is affecting inference in a lot of the realms. And at the same time, inference actually is affecting mechanism design, because we now need to design our experiments in a smart way, because we know that we're going to use them for some further data analysis. And one thing that's really interesting about the rank-based auctions is that we can do a lot of the inferences directly, bypassing a lot of the complicated computation in case where we believe that the agents converge to an equilibrium. And in off-equilibrium settings, things are not as nice. However, we can provide bounds that turn out to be somewhat useful, at least in some of the empirical examples that we've seen, and one that I've showed you earlier. And so the feature of these techniques is really the fact that they're reflecting our desire to create the technologies that are fast and scalable, and at the same time, they are really grounded on the economic theory.
Yeah. Oh, sorry. I'm sorry. I have one here. Susan, question.
So I think this empirical price of anarchy is really, really interesting, and it's something that, in some sense, could be applied more broadly. In that, the computer science theory literature is always doing these worst-case bounds, but there seem like there's many applications where some
So we've been, we were just able to show that we can apply the same techniques to the procurement auction. So the procurement auctions are slightly different because the bidders are bidding their costs, not their values in a sense. So they're kind of the opposite of all of the pictures. So it was a little bit more difficult to establish. But we were able to look at the highway procurement auctions, and it worked beautifully. And actually, we're hoping to apply it to some of your earlier work on timber auctions as well, and just see how well it performs. Because we're getting the bounds that are much, much better than theoretical in most cases, which is, I think, that's kind of one of the exciting findings.